Newton believed that gravity existed, sufficient to send us to the moon at any time. Yet, we feel trapped in time, questioning if we really understand what it is. Newton's discovery is more than a concept, it's a crucial element that might reveal the mysteries of the universe. The universe is presenting the cosmos to us in a manner more untamed than we anticipated. How does Brian Cox's innovative concept challenge our assumptions about time and its potential implications for the way we see things? As we explore Brian Cox's recent, incredible notion of time in the vast universe, we realize there are mysteries surrounding us awaiting resolution. Many of them deal with gravity and time, two important components of our lives. Suppose there was a planet where time behaves strangely, accelerating or decelerating. Additionally, the energy that keeps us on the ground may not be what we think it is. This is where Albert Einstein's theories of relativity become useful. They provide a new perspective on gravity and time. A well-known name, Einstein gave us a novel method to examine the cosmos using his theory of relativity. His research offered insight into how time behaves in various contexts, especially when events occur rapidly. It all began in the early 20th century, when Einstein introduced two major concepts, general and special relativity. In 1905, special relativity altered how we perceive time and space. It states that the same physical laws apply to anyone not accelerating, regardless of how they are moving. This concept leads to phenomena such as time slowing down or stretching under certain conditions. A popular explanation of time in special relativity involves a thought experiment, the light clock. Imagine you're in a spacecraft traveling very fast, near the speed of light. Inside, a beam of light bounces between two mirrors. According to physics, the speed of light never changes. But for an observer outside the vessel, the light appears to take a longer, diagonal path. Because the journey is longer for the external observer, it seems like time is passing more slowly for the person inside the craft. This time difference is known as time dilation. Time moves slower for the person in motion compared to one who is stationary. Being aware of how things change at high speeds isn't just theoretical. Scientists use massive equipment, like the Large Hadron Collider, to accelerate particles near light speed. When things change that quickly, we must think about time differently to get accurate measurements and predictions. Einstein's special relativity changed how we understand motion and time. It suggests that physics laws are the same for everyone, even though that contradicts everyday experiences. For example, we usually think that speed just increases when something moves. But according to Einstein, the speed of light is the ultimate speed limit. Events that appear simultaneous to us may not seem that way to someone moving near light speed. Another concept derived from relativity is length contraction. Moving objects appear shorter when viewed from a stationary position. This, along with the famous equation E equals mc squared, shows how mass and energy are interchangeable. This concept is essential for understanding the behavior of small particles at high speeds and for explaining things like nuclear reactions. Relativity isn't just theoretical, it has practical uses, such as in GPS. GPS satellites send signals to your device, but due to their motion and the difference in gravity, time moves slightly differently for them. If we didn't account for relativity, your location data would be inaccurate. Special relativity teaches us that time is not constant, it depends on motion, which affects our understanding of space and time. Einstein later expanded his theory in 1915 with general relativity, which explores how gravity and the structure of the universe interact. It redefines gravity not as a pulling force, but as the bending of space and time, space-time. Gravity, then, isn't an invisible force. It's the natural path that objects follow through curved spacetime. Think of spacetime as a flexible sheet. A massive object like a planet causes a dip in the sheet. Smaller objects, like balls, roll into the dip, not because of a pulling force, but because of the curve. General relativity can predict the motion of planets and their orbits with remarkable accuracy, better than the traditional Newtonian view. A major event confirming general relativity occurred during the 1919 solar eclipse. Sir Arthur Eddington led a team that observed starlight bending around the sun, just as Einstein predicted. This was powerful evidence supporting the theory. Just as motion affects time, gravity does too. Time passes more slowly near a strong gravitational field. For example, near a black hole, where gravity is extremely intense, time moves slower compared to areas far away from it. Black holes are regions of immense gravity where not even light can escape. The event horizon is the point of no return. Once crossed, everything is pulled into the black hole, illustrating the extreme implications of general relativity. Einstein added the cosmological constant to his equations, believing the universe was static. But when he realized the universe was expanding, he called the constant his biggest blunder. Ironically, this idea is now central to the Big Bang theory. Another consequence of general relativity is gravitational waves, ripples in spacetime caused by massive objects like merging black holes. In 2015, LIGO detected these waves, offering further proof of Einstein's theory. Relativity has been tested repeatedly, from observing light bending around planets to detecting gravitational waves, and it remains robust. While claiming gravity is a fiction might sound absurd, science thrives on challenging assumptions. Some scientists propose alternative ideas, such as modified Newtonian dynamics, MOND, which suggests gravity behaves differently at low speeds, especially in galaxies with dark matter. Others explore the relationship between gravity and dark energy or hypothesize about unknown particles or forces. What's important is that science doesn't dismiss new ideas. Instead, they are rigorously tested. Einstein's four-dimensional theory of spacetime, limited by the speed of light, has also inspired ideas about time travel. Stephen Hawking proposed chronology protection, suggesting that time travel may be theoretically possible but unlikely. Even if gravity is eventually re-explained, current theories haven't been replaced. Challenging ideas is crucial for scientific progress. General relativity remains the most accepted and successful theory of gravity. Relativity endures because it's elegant and effective. According to Einstein, time can vary depending on your motion. Let's see how this plays out in everyday terms. Life occurs in space, and space travel, while exciting, is difficult due to the vast distances. Even with advanced technology, traveling between stars is challenging. Time behaves differently when you move fast. Consider the twin paradox. One twin stays on Earth while the other takes a high-speed journey to a distant star. Upon returning, the space-traveling twin has aged less. Time moved slower for them. This isn't just science fiction, it's a real consequence of Einstein's theory. This effect, called time dilation, has been experimentally confirmed with highly accurate atomic clocks. When one clock is flown around the Earth in an airplane and then compared to a stationary clock on the ground, the traveling clock shows slightly less time has passed. Though the difference is minuscule, it proves Einstein's predictions were correct. In real-world terms, this means time is not an absolute universal constant, it's flexible. It bends and stretches depending on speed and gravity. This idea has changed our understanding of reality itself. The concept that two people can experience time differently depending on their movement or position in a gravitational field was once unimaginable, but today it is scientifically accepted. Let's return to gravity. If gravity is not a force, as Einstein claimed, but rather the warping of spacetime, then objects fall because they are following curved paths within that warped geometry. This notion shifts the way we perceive everyday experiences, from dropping an apple to launching a satellite. Now, consider a place where this warping becomes extreme, a black hole. Near the event horizon, time slows dramatically. If you were to watch someone fall into a black hole, from your viewpoint, they would appear to freeze at the edge, as their time slows infinitely. For them, however, time would continue normally, until they reach the singularity, where the known laws of physics break down. Such environments also push us toward quantum mechanics, which governs the very small. Gravity, despite being the force we experience most directly, is the least understood at the quantum level. Scientists are now trying to bridge the gap between general relativity, which governs the large-scale universe, and quantum mechanics, which governs the tiny particles. This grand quest is known as the search for quantum gravity. Why is this important? Because at the heart of black holes and the beginning of the universe, moments like the Big Bang, both quantum mechanics and gravity are at play. To truly understand these, we need a theory that unifies them. String theory and loop quantum gravity are among the leading contenders, though they remain unproven. Meanwhile, observations are expanding. The James Webb Space Telescope allows us to peer further into space, and deeper into time, than ever before. Since light travels at a finite speed, looking farther means seeing the universe as it was in the past. We're not just exploring space, we're witnessing history itself unfold before our eyes. At the same time, researchers are considering the idea that time itself may be an illusion, a perception that arises from entropy and the direction it flows. According to the second law of thermodynamics, systems tend to move from order to disorder. This progression gives time its arrow, the reason we remember the past but not the future. Brian Cox, and others like him, propose that time might not be a fundamental part of the universe at all, but rather a consequence of deeper physical laws. What if the universe doesn't move through time, but instead exists all at once, with past, present, and future equally real? These questions might seem philosophical, but they are grounded in science. The universe is not only expanding, it is accelerating outward, driven by a mysterious force called dark energy. This expansion has consequences for the structure of spacetime, and ultimately, the fate of the cosmos. Will the universe expand forever? Will it tear itself apart in a big rip? Or will gravity one day halt the expansion and cause everything to collapse in a big crunch? These are not merely hypothetical questions, they are active areas of study that shape how we view everything, from galaxies to atoms to ourselves. Understanding time and gravity isn't just about abstract theories, it's about unlocking our place in the cosmos. Every tick of a clock, every orbit of a planet, every wave of light tells us something about the deeper fabric of reality. Einstein opened the door to a new understanding. Now, scientists like Brian Cox are walking through it, asking deeper questions. What lies beyond the space-time we know? What happens when the fabric of the universe tears, twists, or folds? The quest for these answers isn't over. In fact, it may be just beginning. True, people are being sent to a distant star by humanity. Even if they go quickly, the voyage might take years. Time would seem slower to the astronauts due to the passage of time, but from Earth, more time would go by before time change occurs. Technology, as well as communication on ships, must consider time changes in order to work properly. Space traveling has body issues, such as being struck alone by distance from Earth and space waves. For we observe time in our everyday lives for a long period. GPS requires the correct signal to change periods from satellites. As these satellites are moving, they encounter temporal dilation, so it's crucial to include it into the figures for the readings, which should be precise. Without considering concerns about how driving might be hampered by time changes, why do humans only go in one direction at a time? Our lives are governed by time, moving from the past, from now, to the future. This one-way journey is part of us, so why should we look at this? How disorganized everything is, at entropy linked to the direction of time, tends to increase. Time is being pushed in one direction as it passes. According to the second rule of thermodynamics, entropy will either increase or remain constant, and entropy prefers to increase in closed areas, it never falls on its own. The characteristics of time warrant a more thorough investigation. Time, as we believe it, is closely related to the idea of entropy. Entropy is a basic idea in thermodynamics, the degree of systemic dysfunction. The second law of thermodynamics says that entropy in isolated systems tends to grow with time, resulting in a shift from order to chaos. Not only conduct is governed by principles of tangible systems, but moreover, it offers a structure for comprehending the box learning in a unidirectional flow of time. To demonstrate this, think about the comparison of a castle made out of sand. It symbolizes a low entropy condition, characterized by a high level of order and structure. Over time, as a result of natural phenomena like erosion and wind, eventually the sand castle will turn into a beach pile, a higher entropy state. This transformation is a prime example of the natural propensity of systems to change in the direction of more chaos, supporting the idea that time moves in a single direction from box learning, gravity in the future, and the structure of spacetime. Spacetime, which is built upon the general relativity hypothesis developed by Einstein, is more than just a force, it's an expression of the curved shape of spacetime brought on by energy and mass. Large objects, such as planets and stars, distort the spacetime fabric, and this curvature determines how an item moves, incorporating light. This groundbreaking change in our comprehension occurred as a result of perspective, from considering gravity to be a force, far from acknowledging it as the spacetime geometry's outcome. A powerful illustration of this idea is the measurement of gravity lensing, where far-off stars' light bends around large objects, such as galaxies. This bending is brought on by the galaxy's mass, which bends the spacetime through which the light passes, changing its course. These occurrences provide concrete proof of the dynamic interaction between the organization of mass, energy, and black hole singularities in spacetime. Spacetime is one of the most fascinating aspects of general relativity. Predictions include areas of spacetime where black holes are. Because gravity is so strong, nothing, not even light, may escape from the center of it. The singularity of a black hole is a point where the space's curvature turns into limitless, and what we currently know is the event horizon. It is broken down by physics, denoting the line that nothing may cross, which is able to render black holes both mysterious and fascinating topics of research. Current developments in technology for observation, such as the Event Horizon Telescope, have made it possible for scientists to take pictures of black hole event horizons. These images provide factual information that backs up theoretical models. These findings not only confirm features of general relativity but also provide fresh opportunities to investigate the basic characteristics of spacetime and theoretical gravity. Time travel opportunities and limitations. The idea of time travel has been around as a topic of interest and conjecture in the context of general relativity. Some answers, according to Einstein's field equations, suggest the potential for closed time-like routes and curves in spacetime that may circle back on themselves, making it possible to go back in time. But these fixes often entail unusual circumstances, such as the existence of negative energy or imaginary wormhole-like structures. The timeline was suggested by Stephen Hawking's protective hypothesis, indicating that time may be stopped by the rules of physics to prevent paradoxes from occurring when going back in time and discrepancies as time dilation. A relativistic phenomenon in which time moves at varying speeds for onlookers in experiments relative to motion is validated and has useful applications. Traveling across time in a way similar to science fiction is still purely hypothetical and unverified. Current events and breaking headlines. The use of math in comprehending mathematics in the cosmos acts as a medium through which the expression of natural laws is conveyed. Brian Cox, a physicist, highlights that we learn from our experiences that the rules of nature truly exist. Patterns in the behavior of objects indicate that the best way to communicate these rules is by using mathematical language. This viewpoint highlights the significant relationship between mathematics and the physical world and its structures, demonstrating the ability to forecast using mathematical models to describe natural occurrences. The creation of mathematical models, like general tensor calculus in relativity, has played a key role in developing hypotheses that precisely explain the gravitational behavior of fields and spacetime curvature. These mathematical instruments allow physicists to make accurate forecasts and gain a better understanding of the mechanisms of the universe's expansion. Studies of far-off galaxies show that the cosmos is growing, with galaxies departing from us at speeds according to their distance, as captured in Hubble's law. This suggests there was just one genesis for the cosmos, frequently known as the Big Bang, which has been changing since. The cosmic microwave background radiation offers more proof of the hot, dense beginnings of the universe, providing a glimpse of the early cosmos and bolstering the Big Bang theory model. Recognizing the growth of the cosmos not only illuminates its nature but also provides information about our understanding of cosmic development and the final destiny of the universe. In summary, the interdependence of time, gravity, and the universe shows a universe that is far more complex and interwoven than our daily observations suggest. From the curvature of spacetime controlling the movements of planets to the mysterious characteristics of black holes, these ideas contradict what we think and encourage more in-depth research. As scientific knowledge advances, the interaction between the universe, time, and gravity keeps captivating and growing our understanding of the cosmos. Observing how things we may perceive times in one method, when we go to the mess, like stirring or ice melting. These simple processes highlight how time interacts with matter on a daily basis. Even in our most basic actions, time plays a vital role. However, the way we experience time on Earth is far from the experience of those in space or in more extreme environments. As we delve deeper into the intricacies of the universe, we begin to see that time isn't just a measurement of moments passing, it is a fundamental aspect of how everything exists and operates. The idea of time as an unchanging, linear flow is challenged by the complexities we encounter in scientific exploration. The concept of time dilation, where time passes differently for observers moving at different speeds or in different gravitational fields, illustrates how relative time truly is. It pushes us to reconsider our assumptions about time as something static and universal. Furthermore, as we study more advanced phenomena like black holes and the edges of the universe, time seems to bend and stretch in ways that defy our conventional understanding. Near black holes, time slows down so dramatically that, from an external observer's point of view, an object approaching the event horizon would appear to freeze in place. This paradox underscores just how malleable time is when influenced by massive objects and high speeds. This leads us into the fascinating, though speculative, field of time travel. While current scientific knowledge suggests that traveling backward in time would require overcoming immense physical and theoretical obstacles, the possibility remains tantalizing. Some theories, such as wormholes or the manipulation of spacetime through exotic matter, propose pathways that could allow us to journey through time. However, these concepts remain purely theoretical, and practical applications are far from realization. Still, the very notion of time travel sparks profound questions about the nature of reality. If we could travel back in time, would we be able to change the past? Or would we merely observe it, unable to interfere with events already set in motion? These questions introduce new layers of complexity to our understanding of time, suggesting that time may be less about moments passing and more about interconnected events that cannot be easily altered. The exploration of time, gravity, and the universe continues to push the boundaries of science, philosophy, and human curiosity. As we learn more, we are forced to confront new questions that challenge our deepest assumptions about the universe and our place within it. Time, it seems, is not just a ticking clock, it is a dynamic force that shapes everything from the motion of the stars to the unfolding of our daily lives. In the future, as technology and theory advance, we may find that the mysteries of time and the universe are even more intricate than we can imagine today. What we once thought of as immutable truths may reveal themselves to be mere stepping stones toward a deeper, more profound understanding of the cosmos. Time, in the end, may not be the unyielding constant we believe it to be, but rather a complex, fluid concept that is intricately linked to the very fabric of reality itself.